Okay, so thanks for your patience. Yeah, so last time we talked about univariate and multilinear Lagrange interpolation. Okay, and I'll try to just review this really quickly. So the idea is here that there's sort of, I guess, a theorem. I'll just cover everything in the univariate case. So let capital H, which is called an interpolating set, be any subset of the finite field we want to work over, say of size n. So univariate Lagrange interpolation says there is a unique polynomial P with the following behavior. Actually, let me, all right, sort of should have prepared a little more. You think after I presented this last night, I'd be better. So let's say let V0 to Vn minus 1 be any n field elements. So there is a unique polynomial P with the following behavior. So it maps the ith element of H to the ith value Vi. Of degree n minus 1. Okay, so another way of saying this theorem is like, just as you can uniquely specify a degree n minus 1 polynomial by its n coefficients, you could also uniquely specify it by saying, hey, here are n points in the field, and telling me exactly what value the polynomial should take at each of those n points. Okay, so Lagrange interpolation is all about specifying a polynomial via its evaluations rather than like its coefficients in the standard monomial basis. And moreover, we saw an algorithm that takes as input like a specification of the interpolating set. So just like a list of all elements in the interpolating set or whatever, H as input. Some interpolating sets have succincter specifications than just listing all their elements, but it's not really important right now. Takes the values as input and take and a desired evaluation point R, and outputs the interpolating polynomial evaluated at R in order n time. Okay, and the way this algorithm proceeded, or the way we presented it, is like, first we just gave an explicit expression for the polynomial as like a sum over all points in the interpolating set of the desired evaluation at that point times something called the Lagrange basis polynomial for that point. Let's say evaluated at, let me call this y. Yeah. So this was an explicit expression for the interpolating polynomial, that is this polynomial P that has the desired point-by-point behavior. Right, and I won't cover it in detail, but basically like this polynomial was meant to sort of pick out like just this particular element of the interpolating set and kind of kill everything else in the interpolating set. And then this coefficient was chosen just to make sure the polynomial does exactly the right thing at the picked out point, so that xi gets mapped to vi. So we gave this explicit expression for the interpolating polynomial P, and then we showed how to evaluate this expression at the desired evaluation point R in linear time. So that was univariate Lagrange interpolation, and we saw an analog for multilinear Lagrange interpolation. In that case, the interpolating set H is not a subset of the field, but rather it typically is, doesn't have to be, but 0, 1 to the L if we're dealing with L-variate polynomials, L-variate multilinear polynomials. As a reminder, multilinear means the polynomial has degree at most 1 in each of its L variables. And as we'll see, the interactive proofs we designed, namely the sum check protocol we're going to see today, it's not really important that we use 0, 1 to the L. What's important is that we use some product set. So like B to the L for some subset B of the field. So product sets are important. In fact, you're to have an interpolating set for L-variate polynomials, meaning to have like an analog of this theorem I wrote here being true, about there being a unique interpolating polynomial. You really need to use product sets. So any subset of a finite field of size n is an interpolating set for degree n-1 polynomials that are univariate. But when you move to multivariate polynomials, the interpolating set's typically a product set. Question.
Yeah. So basically, we would have a tuple of L length here, is what we're saying.
Yeah. So when we go to like each element of the interpolating set. Okay, so an L-variate polynomial, like the input to that polynomial is like just a list of, L field elements. And if you want to do, what's happening is, I'll just write out the theorem in the general case for product sets here. So let me just write it out. I think it's worth taking the 2 minutes to do it. Okay, so let B be a subset of the field. Let's say B has size D. And let's say we're dealing with L variables. So note that the size of the product set B to the L is D to the L. So here B to the L is, the set of all L tuples where each entry of the tuple is from B. So you have L entries and D choices for each entry. And let's say I have values now indexed from 1. Sorry, just switch from 0 indexing to 1 indexing, V1, V2 up to VD to the L values from the field. So the statement is there is a unique L-variate polynomial of degree at most, I guess it would be D-1 in each variable, such that for x1 up to xd to the L in B to the L, P of xi equals vi. So the multilinear case just had B equal to 0, 1. But there's nothing special about B equals 0, 1. So you could have, if you want B to still have size 2, you could have BB minus 1, 1. Actually, some works actually do that. You could have BB, any field element, comma, any other field element. And you could also have BB bigger than having size 2. Which actually I think I mentioned, but I don't know which group I rambled about this in probably last week, maybe 2 weeks ago. I actually think people should do that more as recursion, snark recursion becomes more important. These interactive proofs applied to L-variate polynomials, they have 1 round, and we're going to see this today with the subject protocol. They have 1 round for each of the L variables typically. There are ways you can play with it to have fewer rounds, but the effect is the same as what I'm about to say. By using a set of size bigger than 2, you can reduce the number of variables, but increase the degree D in each variable. And what that will do when you apply interactive proofs like the sum check protocol to the resulting interpolating polynomials is the number of rounds will fall, but the proof size in each round will go up. But if you're ultimately going to take the resulting interactive proof-based snark and compose it with another snark, it actually can be a good trade-off, I believe, although no one has actually gone out and done this. Because we're going to get a snark from these interactive proofs, we're going to apply the Fiat-Shamir transformation to remove the interaction. And that requires a cryptographic hash evaluation for each round of the interactive protocol. And that gets nasty when you want to compose snarks, because you have to take the verifier of one snark and represent it as a circuit to apply the prover of the other snark to. So I actually think there are benefits to kind of making the proofs for these interactive proofs a little bit bigger while bringing the number of rounds down, so that applying fiat Shamir to remove the interaction and then turn the resulting verifier into a circuit, like the bottleneck should actually be the hash evaluations from fiat Shamir in some cases. So it'd be a valuable trade-off to actually have bigger proofs but fewer rounds. Did that answer the question? Do you want me to say anything else?
Yeah, no, this is very helpful. I'm just thinking through what you said. So I guess the final follow-up question and why I was asking is, you know, if you look at the circuit satisfiability, you basically have an address for every gate, and each gate can be evaluated within the finite field. And was just trying to figure out how we go from the circuit satisfiability to a polynomial with that addressing system.
Yeah, great. So so we're jumping way ahead here, but I think no, it's good. I think it's a good conversation to have. So in the snarks or interactive proofs you're referring to, what they'll typically do is they'll assign each gate a binary label. So if there are like S gates in the circuit, each gate will be in like 0, 1 to the log base 2 of S, right? Because you can assign, there are like S unique binary strings of length log base 2 of S. And then you'll sort of define like a polynomial whose input, if the input is in 0, 1 to the log base 2 of S, so this is a log base 2 of S varied polynomial, should spit out like the value of gate A in the circuit, when evaluated on the witness or whatever. And what I'm saying you should do instead, and eventually this will get very natural if in this reading group, but it takes a little bit to get used to it, is instead the gate label shouldn't be in 0, 1 to the log S. It should be in, say, it doesn't like 0, 1 up to D minus 1 in the to the log D of S. So for example, I don't know if you want to make this a little, if you don't like log D of S, log base D of S, I don't know, 0, 1, 2, 3 to the log base 4 of S, which would actually be 1/2 log base 2 of S. So you cut the number of variables by factor 2. And then you define the polynomial through, it's literally like essentially the same procedure as the multilinear Lagrange interpolation we saw last time. But you would define a polynomial of degree 3 in each variable. And it would have, now, log base 4 of S, which again is 1/2 log base 2 of S variables. And we would ensure that, so now now if you feed this polynomial a gate label, but now gate labels are in 0, 1, 2, 3 to the log base 4 of S, rather than 0, 1 to the log base 2 of S, you'd insist that it spits out like the value of gate A. So the algorithms we saw last time to do interpolation, it's for multilinear, it's like the same algorithm this time. It's just, rather than the resulting polynomial we're interpolating having degree 1 in each variable, it has degree 3 in each variable. Does that make sense?
To some extent, yeah. And I know we'll probably touch on it later. So you're essentially taking this circuit where all the values. So is there one polynomial coming out of it? I think that's my key question.
Oh yeah. In all of these snarks, there's one polynomial coming out of the circuit, or let me just leave it at that. Yeah, and the question is just, do you want that polynomial? Do you like interpolate it over the 0, 1 to the L, where L is like log base 2 of the circuit size, or do you interpolate it over a different product set? For example, 0, 1, 2, 3 to the L, where L is now like log base 4 of circuit size. And there's just a trade-off in the number of variables and the degree of the polynomial. Like ideally, we'd like them both to be small, because certain costs of our interactive proofs and snarks grow with both the degree and the number of variables. But they're, they sort of, different costs depend on different things. So there could be some benefit to, having more variables and lower degree, or fewer variables and higher degree, as you sort of work through all of the possibilities, as you go from interactive proofs to snarks to recursive snarks and blah, blah, blah. Yeah, maybe I'll just mention like the Lagrange basis polynomials for multilinear. They look like the following. So I don't know, the basis, let me say, 4 variables, and let me look at like sort of the Lagrange basis polynomial that's meant to pick out the bit vector 0, 1, 1, 0, I guess. So this would be like the basis polynomial for that, as a reminder, R1, R2, R3, R4 would have been 1 minus R1 times R2 times R3 times 1 minus R4, right? And the point is, this factor is, mapping 0 to 1 and 1 to 0. So it sort of ensures that the first, if you feed it a Boolean input, it makes sure that the first bit is 0 and not 1. And this factor makes sure the second bit is 1 but not 0. The third bit is 1 but not 0. And the fourth bit is 0 but not 1. And just for illustration, if your interpolating set was not 0, 1 to the 4, but rather say 0, 1, 2 to the 4, the basis polynomial would have to change. Basically, rather than dealing with either 1 minus x1 versus x1, where this maps 0 to 1 and 1 to 0, and this maps 1 to 0 and 0 to 0 and 1 to 1. Instead, your basis polynomial would be, you'd have 3 options, whether you're picking out 0, 1, or 2. The one that picks out 0 would be, we want to kill 1, we want to kill 2, and then we want 0 to map to 1 rather than 2. So this would be the first basis polynomial. This would be the second would, if we want, so this picks out 0, kills 1 and 2. If we want to pick out 1 and kill 0 and 2, so killing 0 would mean x1, killing 2 again is 2 minus x1, and then we want 1 to map to 1, so actually we're good there because 1 times 2 minus 1 is just 1. And then the last one, so this, this picks out 1, kills 0 and 2, and then the last one is we want to kill 1 and 0. And make sure 2 maps to 1. So I guess we divide by -2. Yeah, and then so the corresponding basis polynomial in that case, I guess, would be you want to pick out 0. So you'd be, this would become. So first we want to pick out 0. So we'd have 1 minus R1 times 2 minus R1 over 2. Then we want to pick out 1. So we'd have R2 times 2 minus R2. Then we want to pick out 1 again for the third variable. And then we want to pick out 0 again for the fourth variable. 1 minus R4, 2 minus R4 over 2. Yeah, so if your interpolating set were 0, 1, 2 to the fourth, like this would be the Lagrange basis polynomial that picks out this particular element of 0, 1, 2 to the fourth. Okay, so that was obviously really quick. I actually expect many of you maybe didn't follow that, but I was just trying to give a sense of how Lagrange interpolation would change if you didn't look to interpolate a multilinear polynomial over the Boolean hypercube, but rather look to interpolate a slightly higher degree multivariate polynomial over a product set, like 0, 1, 2 to the fourth instead of 0, 1 to the fourth. Okay. Any other questions right now? And it's okay if you didn't follow all of this. We'll get more practice with these multivariate polynomials as we go. Cool. Okay. So then let us talk about interactive proofs. I think I was about this slow last night too. Yeah, this presentation just generally took longer than I thought it would, but I think that's okay. So when telling you what is an interactive proof, I think it's helpful to have a specific application in mind just to make things concrete. So that application I'm just as a story sort of, I'm going to bring up like commercial cloud computing. So imagine like you who only have a laptop, hire a commercial cloud computing service to store and process your data because you need to do heftier calculations than your laptop is capable of. So I'm going to call you the verifier and the cloud computer the prover. So the idea is you might ship a bunch of data up to the cloud. Okay, the cloud is going to store all that data. If you're using an interactive proof to check that the cloud's doing everything correctly, you actually won't have to store all that data. You can keep around a tiny summary of the data. We'll see that this is possible in our interactive proofs. And then later, you're going to ask the cloud like a question about your data. This will, in practice, often be in the form of a computer program you want the cloud to run on your data. And the cloud comes back and says, hey, I ran your computer program on your data, and this was the answer. But you don't trust the cloud, so you start interrogating it, sending a sequence of challenges, getting a sequence of responses. And hopefully, after not too many challenges and responses, you are ready to stop interrogating the cloud and either accept its answer as valid or reject it as invalid. Okay. And any interactive proof has to satisfy two properties called completeness and soundness. So completeness says if the cloud is honest, meaning it returns the correct answer and follows the prescribed protocol in responding to the challenges, then the verifier will accept. Now, all of our interactive proofs that we'll see have what's called perfect completeness, meaning the verifier always accepts the claim of an honest prover. So probability 1. In general, you could allow some small probability that the verifier rejects a valid claim. But we'll just naturally, all of our protocols will not have that issue. That possibility will never arise. And then the other property is called soundness. This is a security property. This says if the returned answer by the prover is wrong, then the verifier will reject with high probability. So let's say with probability at least 1 minus something called the soundness error, delta S. So we want that soundness error to be small. Okay, and in an interactive proof, this soundness property is supposed to hold even if the cheating prover is computationally unbounded and working insanely hard to try to come up with convincing responses to the challenges. Now, if soundness only holds against computationally bounded provers, it's called not an interactive proof, but rather an interactive argument. So let me just write that out. Like polynomial time cheating provers. It's not an interactive proof. It's called an interactive argument. So the idea is basically interactive proofs. It is an interactive argument. Interactive proofs don't use cryptography. They are secure, even if the prover, works in an unbounded amount of time trying to compute convincing responses. Soundness in this case is called information theoretic soundness or statistical soundness. Those terms are synonymous, statistical or information theoretic. Whereas if the proof system, although it really should be called an argument system, uses cryptography, that's called computational soundness. So the idea then is if the prover can break some crypto system, if it can figure out the verifier's private key or something, it actually could find a convincing quote proof of a false statement. So with arguments, it's like convincing proofs are kind of, they exist, but they're hard to find. Whereas with interactive proofs, convincing proofs, quote, and again, the proofs are interactive here, but they just don't exist at all. There's just even inefficient provers are going to get caught with high probability. Okay, in practice, typically our interactive proofs will be defined over some finite field, and delta S, the soundness error, will be at most, typically it's some polylog. It can depend. Some not terribly large quantity that grows with the complexity of the statement being proven. So let me just call that complexity n. Kind of vaguely, I won't tell you what n is, but here's the key point: over the field size. Okay, so if we work over, say, like a 256-bit field, this soundness error is really, really tiny. Like, really, you can just ignore it. The prover will basically never in the history of the universe ever get lucky and convince the verifier to accept a false statement. Okay, but in snarkland, people are sort of trying to work over smaller and smaller fields, and then you do have to reflect on the fact that this soundness error might not actually be negligible. It might be too large. In which case, the soundness error can be reduced by repeating parts of the protocol and sort of making the prover get lucky multiple times. And that can be a little bit subtle, actually, but let's stop the discussion there for now. Okay, so those are interactive proofs. I'm going to raise some subtleties about the interactive proof model, which I don't want to spend too much time on because those subtleties will actually never really arise in this reading group, but I do think they sort of need to be mentioned so you're aware of them if you're ever like reading a paper about interactive proofs. But let me just pause and see if anyone wants to ask anything, and then I'll mention some subtleties about interactive proofs when all questions are done. Any questions? Okay. Okay. So the first subtlety I want to discuss, which last night took a while to get through, but yeah, so I'll try to make it a little faster today, is interactive proofs. I'm going to call them IPs for functions versus languages. Okay, first let me tell you what is a language. Actually, let me start with decision problems. So decision problems are problems where the output is always yes or no, or equivalent like 0 or 1, or true or false. There's only two possible outputs. So let's just say that the input domain for the function for the decision problem is 0, 1 to the n. It doesn't really matter what the input domain is. But let me say that the output is either yes or no, 0, 1, true or false. That's a decision problem. So we think of inputs mapping to 1 as yes instances, and inputs mapping to 0 as no instances. Yes and true are sort of logical true are sort of the same. F of x equals 1 is no or false. Okay, and a language just refers to like all language. So just refers to all the yes instances. So a language is just like a subset of strings, namely those strings that map to that f maps to yes. Okay, and in an interactive proof for a language, I'm bringing this up because if you read, like old papers on interactive proofs, this is how they define things. The completeness notion only refers to yes instances. So it says if x is a yes instance, then there's a prover strategy that convinces the verifier to accept. Say with perfect completeness, that would be probability 1. But completeness just doesn't refer to no instances at all, which is what's in contrast to how I define interactive proofs for functions. And then soundness only refers to no instances. So if f of x equals 0, then for any proving strategy P, V will reject with probability 1 minus delta S, at least. So what's happening here, the reason this definition was introduced is, as true mathematicians, the theoretical computer scientists introducing interactive proofs, we're thinking of the yes instances as like the true statements. Think of it as just like, the mathematical theorems that are actually true. And then completeness is saying like, any true for any true theorem, there should be a convincing proof of its veracity. And soundness is saying for any false theorem, there should be no convincing quote proof of its veracity because it's not true. That was the idea. And in particular, for interactive proofs for languages, it's not required. This is the key difference from functions. It's not required that false statements, meaning no instances, have convincing proofs of their knownness. And I think in practice, in most applications in practice, like this is not really what you want, right? Like you want that, you just want the prover to compute some function of your data. You don't, for any possible output of that function, you want to be convinced that the prover did the computation correctly. So like in practice, this sort of asymmetric, treating yes instances and no instances differently sort of is not quite what you want. That said, in like snark applications, this is kind of what derailed me into a rambling, confusing, tangent last night. In most snark applications, like the prover is choosing like a true statement to prove. So in a sense, like completeness does only have to apply, like only true statements need convincing proofs. Like the same thing still holds. It's just, the true statements that the prover's claiming in snark land, typically like the prover knows a witness that causes a circuit to output some value, right? And like that's a true statement, so you only need a convincing proof for the true statements, of course, like just as in this asymmetric case. But in terms, that the prover knows a witness out, causing the circuit to output what that output is, which is the sort of thing that is more like how I've defined interactive proofs for functions. So I don't want to dwell on this too much. I just wanted to mention this sort of distinction between interactive proofs for languages and functions. In fact, an interactive proof for the function f is actually equivalent to an IP for the language of strings of the form x comma f of x. Right. So, this distinction is not really like a meaningful one. It's purely a distinction in like just kind of the definition of completeness and soundness. But basically, if I can only prove yes instances where, where our yes are yes, where my yes instances are of the form x f of x, right, then proving that x f of x is a yes instance is just equivalent to proving that, f of x is indeed f applied to x, which is exactly what you want in a interactive proof for the function f. Okay, and just final comments. If you've ever seen the complexity classes P and NP, P and NP and co-NP, all right. These complexity, and if you haven't, don't worry about it. These complexity classes have exactly this asymmetry about languages. So NP is the class of all languages, where yes instances have convincing proofs of their yes instance of their yesness. Where the proofs can be checked in efficiently, meaning polynomial time. And co-NP is the same thing, but where no instances have convincing proofs of their knownness. Okay, and having a convincing proof of yesness does not necessarily imply, to the best of our knowledge and belief, having a convincing proof of knownness. So, for example, a classical problem in NP is called 3-SAT, which says, or circuit SAT, let's say, given a circuit, is there an input to the circuit that causes the circuit to output true or 1? And there is a convincing proof of yesness there, which is simply provide the satisfying assignment. Like that's the witness, provide the witness. And the verifier just evaluates the circuit on the witness and confirms it outputs 1. Okay, but it's not clear. We don't believe circuit sat is in co-NP. It's not clear if there are no satisfying assignments to the circuit, how one could possibly prove that in fact there are not, and it's like proving a negative. Like, if there is a satisfying assignment, you can prove there is one by just providing it. If there's not a satisfying assignment, how are you going to quickly, prove that there isn't one, right? It's like, if I give you an assignment, the verifier can certainly check it's not satisfying, but that doesn't mean there's not some other one out there. So circuit sat is not believed to be in co-NP. So yeah, if you study complexity theory, like this difference between, how I've defined completeness and soundness for functions versus for languages really comes up because complexity theorists like to deal with languages. Okay, I don't want to spend much more time on that, but let me just stop and see if there are any questions.
Like, I wonder if this is related to like Turing machines and lambda calculus, because like function sounds like more like lambda calculus definitions, and like language sounds more like Turing machines. I don't really know, but
yeah, I guess I would say like it's known that like lambda, the class of functions computable in the lambda calculus is equivalent to the class of functions computable by Turing machines. And in computability means you like don't really care about runtime. You just care like, do you ever get the answer out of the machine or something? So this sort of asymmetry between yes instances and no instances like doesn't really matter if you don't care about runtime, right? Because right, like you can determine, like as long as you can determine if the answer is yes when it is yes, like you can also determine if the answer is no by just running the algorithm that sort of checks for yesness, and like if it doesn't come back, in the appropriate time bound and say the answer is yes, then the answer is no. Yeah, I think probably this sort of thing does not arise too much in computability theory, which is normally where you see lambda calculus. Well, you also see lambda calculus in like programming language design. I don't know much about either, so maybe I'll just leave it there.
Yeah, makes sense. Thanks.
Yeah, great. Yeah, thanks for the questions. Let's see. Other questions? Okay, cool. So I'll just briefly mention that like the model of interactive proofs is pretty robust to tweaks in it. In fact, there are transformations known that will turn an interactive proof with like, under one definition into a quote efficient interactive proof under a variant definition. Now I do want to be clear, these transformations do not perfectly preserve efficiency of the interactive proof, especially when looking at prover time. But it is worth just mentioning a couple of them. So it's known that if you have an interactive proof with imperfect completeness, you can turn it into one with perfect completeness, and you'll roughly preserve the verifier time. And there's also a transformation from what's called private coin to public coin. And this I do want to describe very briefly, not how the transformation works, but just what public coin and private coin means. So public coin means all verifier challenges in the interactive proof are just like uniform randomness. So in practice, this means uniform random field elements because all of our interactive proofs will wind up working over fields. So in particular, you can imagine like as soon as the verifier like chooses another random field element, it's just like immediately revealed to the prover as a challenge. That's a public coin protocol. Private coin protocol is, you can define it a couple ways, but basically you can imagine like the verifier might toss a bunch of coins at the start and not reveal them to the prover. And then its challenges can depend on those private coins, but not literally just be the coin tosses. And not reveal them to P. Challenges might not just be the coin tosses. And it's known that there's you can take any private coin interactive proof and turn it into a public coin one. Both transformations do not preserve prover time, but they do preserve verifier time in a rough sense. So if the verifier runs in what's called polynomial time in the original protocol, in the transformed one, it still will run in polynomial time. So do not preserve prover time at all. They can have an exponential blow up in prover time and only approximately preserve verifier time. Okay, so in all of the interactive proofs we design, they will just naturally have perfect completeness and naturally be public coin. So you don't have to worry about these transformations. The main point is, I guess, that the fact that the interactive proof model, like its power, at least if you're just focused on polynomial time verifiers, is sort of robust to these changes, like imperfect completeness or perfect completeness, private coin or public coin, is a good indication that the model is like really capturing something important. It's not like a brittle model where if you like change a little thing, like its power wildly and that actually goes back to Turing machines have a similar property where if you only care about polynomial runtime as your notion of efficiency for Turing machines, the details of how you define Turing machines don't really matter. And random access machines and Turing machines and all sorts of other variant models all have like the notion of polynomial time for them is like all equivalent. So that's what we look for in models as an indication that the model is really capturing a fundamental phenomenon, is not just like some idiosyncratic thing that's very specific to the particular definition, details you settle on. Okay, and the reason public coin turns out to be important for us is because of the Fiat-Shamir transformation. So the Fiat-Shamir transformation is a way to basically just remove interaction from any public coin interactive protocol. And we'll be talking about that a lot more, especially about its security. So it's a good thing that all of our interactive proofs are sort of naturally public coin. It means we can get rid of the interaction if we're willing to use cryptography via the Fiat-Shamir transformation. Okay, that's everything I had to say about interactive proofs. I'm going to pause for questions again, and then move to the sum check protocol. Any questions? All right, so I'm actually running about 10 minutes ahead of last night, if you can believe it. So that means maybe I'll try to be a little less rushed in covering this. Then I want to get through as much as I can. If anyone has to go at the hour, and then kind of after the hour, I'll try to make sure I slow down a bit. So the sum check protocol is our first interactive proof. And in fact, I think it's like the main hammer you need to know, not just for interactive proofs. I actually think eventually snarks based on this protocol will kind of become really, really popular. I'm trying to convince people, including possibly you, if I'm effective, of the benefits of this protocol. So let me describe the problem this protocol solves. It's kind of a funny problem. When you first see it, you'll be like, that's a weird problem. Like, what's that going to capture? But we'll see next time, like a bunch of applications, like as long as you're a little bit clever, you can kind of map all sorts of problems into the sum check protocol that on their face, like don't look anything like an instance of the sum check protocol. So here's the problem. The verifier is handed, and let me just be vague about what that means, but the verifier is given as input somehow an L-variate polynomial G. And the goal, let's say the G is defined over a field F. So let's say that means its inputs are, L field elements specifying input to the polynomial, and it spits out an evaluation, which is just one field element. And the verifier's goal is to basically sum up all of G's evaluations over the Boolean hypercube. So sum over all x in the Boolean hypercube, 0, 1 to the L of G of x. Okay, and the way to think about this is like the verifier, of course, could compute the sum on its own with 2 to the L evaluations of G, right? It can just evaluate G at each of these X's and sum the results. So this in time, let's say 2 to the L times how long it takes to evaluate G at any one of these inputs. And you should think of that as like too expensive. The verifier doesn't want to do that work on its own. Okay, so what we're going to do is basically force the prover to do that work. So sum check lets V force the prover to tell it the sum, force P to tell it the answer. And checking the proof is much easier than just solving the problem on its own. So V's work in the sum check protocol is order L. L is the number of variables, remember. Order L field operations plus the time to evaluate G just at a single point. Okay, some quick comments here. This order L. Okay, what it really is something like L times the degree of G in each variable. So I should have said, let's just for concreteness, let's assume that the degree of G in each variable is 2. That'll actually be the case in many of our applications of SumCheck. So G might have many, many variables. Think, I don't know, 100 variables, but the degree of G in each variable is 2. In which case, the verifier's work really is, order L. In general, this is hiding a constant that depends on the degree of G in each variable. So if G had degree like, very large in each variable, then this order L is a lie because the big O notation is hiding. It's really like order D times L, where D is the degree of G in each variable. Okay, and so but let's just think of the degree of G in each variable as being 2, and let's think of L as like small enough that we don't really care about this order L work. In which case, the SumCheck protocol from the verifier's perspective is sort of reducing the work from 2 to the L evaluations of G down to just 1 evaluation of G. Something to note is that the evaluation of G that the verifier needs in the SumCheck protocol is actually G of R for an R chosen at random from field to the L, whereas these evaluations being summed are very sort of special evaluations. They're in 0, 1 to the L. Okay, so sometimes it's like much easier to evaluate G, it depends on G, at these Boolean inputs rather than compared to at general inputs from the field. And so you should be aware of that. The verifier in the SumCheck protocol has to evaluate G at one input, but that input is like from the whole field, not just from the Boolean set. Okay. And then I think I'm mostly going to wait till next week to talk about prover time, but I'll just tell you that P's time is at most order 2 to the L times the evaluation time of G. And note that in general, this is only a constant factor slower than what's required just to solve the problem. Okay, now this gets a little bit subtle. I'll tell you after I finish writing that sentence out why. Only constant factor slower than solving the problem. So if we don't assume anything about the polynomial G, like we sort of assume it has no structure or something, then the fastest way to solve the problem really is like you just can't do better than literally evaluate G at each of the 2 to the L inputs and sum the results. But in applications of the SumCheck protocol, G will actually be structured. And in that case, there might be a way to compute the answer faster than just naively, going over every term of the sum, evaluating G at that term and summing the results. Now, typically in that situation where there's a faster way to solve this problem than the naive way, there's also a faster way to implement the prover. So typically, and this is sort of this is a very informal statement because typically it doesn't really mean anything formally. But in most of our applications, actually, if the problem can be computed faster than 2 to the L evaluations of G, then the prover can run faster as well. So if the true answer can be computed faster, let's just say in time t, typically, I'll just say often, P can still run in time order t. And sometimes even faster than that, sometimes t plus little ot. And we'll come to that, like we'll talk about a little bit about matrix multiplication and what I call super efficient interactive proofs, where the prover just solves the problem and then does a low order amount of extra work to prove it's correct. Okay, so that is SumCheck. That's the problem it solves and its costs. Oh, I guess I forgot to tell you the proof size. The proof size is like the same as the verifier time. I said the verifier runs in time like order L plus 1 evaluation of G. And that order L field elements, is the proof size too. And I also forgot to mention, so there are L rounds. I'll write this one down. There are L rounds, 1 per variable of G. And in each round, what the prover sends, it's kind of funny if you've never seen it before. The prover sends a univariate polynomial. I'll call it, if the round is J, the prover sends a univariate polynomial, Sj, of degree at most 2. Okay, which means you could think of the prover in round J could just send the 3 coefficients of Sj. Like if Sj is like a plus bx plus cx squared, it could just send a, b, and c, so 3 field elements. But it turns out if you want to implement the prover quickly, it turns out to be really convenient for the prover not to send the coefficients in the standard monomial basis, but instead to send 3 evaluations of the polynomial. And in fact, if you really, really want to optimize every little thing about the prover, the best evaluations to choose turns out to typically be, I think, 0, 1, and -1. That really, saves like some constant factors in the prover time because it can kind of reuse work between the 3 evaluations. Anyway, and yeah, a lot of people when I cover the SumCheck protocol kind of are confused. Like, hey, like I understand that a degree 2 polynomial could be specified either by its 3 coefficients in the standard basis or by its evaluations over any interpolating set of size 3, such as the set -1, 0, 1. But they're just it's just if you've just seen polynomial interpolation for the first time, like we did last week, it just takes some getting used to that the verifier can easily go from these 3 evaluations to what it needs to actually check the prover's messages in the SumCheck protocol, which turns out to be an evaluation of the polynomial sent in round J at a random point. And fortunately, just last week, we saw an efficient algorithm to go from, the evaluations of a desired polynomial over an interpolating set to the evaluation of that same polynomial at any desired input in the field. Actually, this polynomial is of such low degree just 2, that you don't even need to use like any non-trivial interpolation algorithm, like even quadratic time interpolation. Quadratic time in the degree of the polynomial applied to a degree 2 polynomial. It's like quadratic in degree 2 is still just like time 4 or something, time 9. It's their 3 coefficients. The square of that is 9. So you don't even necessarily, if you don't care about constant factors, you don't even have to use like intelligent algorithms to go from these 3 evaluations to the desired evaluation the verifier needs. Okay, yeah, I think that's everything I had to say about kind of the cost of the SumCheck protocol and how to think about the prover's messages before I actually just tell you what those messages are. So let me just pause here and see if anyone has any questions about the problem that SumCheck solves or the cost of the protocol. No questions? Okay, let's see the protocol then. So in round one, like let's say the prover starts by, at the very start of the protocol, by just sending the claimed answer C. Okay, the verifier doesn't trust if the claimed answer is equal to the true answer. So in round one, the prover sends the univariate polynomial S1 of degree at most 2. Remember, I'm just saying 2 is coming in just because I'm assuming that the degree of G in each variable is 2. And if the prover's honest, then S1 will equal the following polynomial. Let me call it H1. So this is obtained by basically taking the problem the prover's supposed to solve, which means kind of summing over all Boolean inputs to G, but kind of cutting out that first variable. So rather than summing over x1 to xl and 0, 1 to the L, it sums over x2 to xl and 0, 1 to the L minus 1. Okay, and then it just leaves the first variable kind of unbound. So it just doesn't sum over that first variable. Okay. So what's happening here is if the prover's honest, there's still like a huge number of terms in the sum, right? There's 2 to the L divided by 2 terms in the sum. So it's still a really big sum. Computing this sum still is like, it's way more than the verifier would want to do on its own. But the point is, while there's a huge number of terms in this sum, because G has degree 2 in its first variable, each term in this sum is a degree 2 polynomial in X1. And if you take, it doesn't matter how many degree 2 polynomials you sum up, the result is still just a degree 2 polynomial. Right? So I'm taking 2 to the L over 2 degree 2 polynomials in one variable. I'm summing them all up. That gives me what the honest prover would send in round 1. Okay. Now, we defined this polynomial H1 like explicitly so that the following holds. So if the prover is honest and S1 equals H1, then the true answer will be simply S1 of 0 plus S1 of 1. Right? So if the prover's honest, so in a different color, I'll say, pick, I don't know, black. Black looks a lot like blue, so this did not help. Let me switch it in color, brown. So if P is honest, this equals the true answer, which is H1 of 0 plus H1 of 1. Okay. So that means at this point in the protocol, I'll leave this brown because it's like a conceptual point instead of just telling you how the protocol proceeds. This means assuming this check passes, then the verifier is convinced, like it's totally safe for the verifier to believe that C is the correct answer, so long as, and this is key, so long as S1 is what it should be. Okay, but unfortunately, V still has to check that S1 equals H1. Remember, these are polynomials, so S1 of X1 equals H1 of X1, if you want me to write out the variables there. Okay, so the question is, so conceptually at this point in the protocol, like checking the correctness of the prover's original claim has kind of been reduced to checking that S1 equals what it should be, namely H1. How does the verifier do that? And now we're back to describing how the protocol proceeds. So let me switch back to blue. So what the verifier is going to do is just pick a random field element, R1, send it to the prover, and now V is going to confirm that, and this is what the rest of the protocol is devoted to. So V will confirm that S1 evaluated just at R1 equals H1 evaluated just at R1. Okay, and the reason this is enough is by this like univariate version of Schwartz-Zippel, which you actually probably saw like in 8th grade. Okay, like that is if S1 and H1 are the same polynomial as the prover is claiming they are, then obviously if you evaluate them both at R1, they'll spit out the same thing. Okay, but they're both degree 2 polynomials. So if they're not the same polynomial, they can only agree at most like 2 points or something like that. I always forget if it's 2 or 1 or 3. I can never remember. So the point is, if S1 does not equal H1, then with overwhelming probability over the choice of R1, probability at least prob over R1, that S1 of R1 does not equal H1 of R1. If S1 and H1 are not the same polynomial, that probability is at most something like 2 over field size. Yeah, so what's happening here is the verifier needs to check that S1 of X1 and H1 of X1 are the same polynomial. The way it's going to check that is just by evaluating them both at the same randomly chosen input. And if that check passes, it's safe for the verifier to believe they're actually the same polynomial. So this technique comes up. We already saw this in fingerprinting, like three meetings ago. So this same idea just comes up over and over and over again in SNARK designed and interactive proofs. Okay, but now so at this point, the verifier needs to compute S1 of R1 and H1 of R1. And, S1 of R1 is no problem. Like the prover sent it S1. And we talked about how, the verifier can compute S1 of R1 on its own. If S1 was specified via its evaluations, you need to use Lagrange interpolation. If it's sent via its coefficients, it's even easier for the verifier to evaluate S1 of R1. So V can compute that on its own with just a handful of field operations, something like, I don't know, like 6 field operations or something. The big problem is H1 of R1. So let me write out what that is. So the verifier cannot compute H1 of R1 on its own. So H1 of R1 is the sum over X2 to XL in the Boolean hypercube, 0, 1 to the L minus 1 of G, with the first variable fixed to R1, and then the last variables being X2 to XL. Okay, so this is, a sum over 2 to the L over 2 terms. It's better than 2 to the L terms as the original sum was, but it's still way too much work for the verifier. So the verifier is not going to do this on its own. But fortunately, we can just use the sum check protocol. So, this is just a degree 2 polynomial in X2 up to XL. And the number of variables is now L minus 1 instead of L. Okay, so we're just going to apply sum check again just to a polynomial in one fewer variable. Okay, so let me say maybe I'll call it Q. I don't know, like Q of X1 of X2 to XL be G with the first variable fixed to R1. Let's just apply sum check to Q to compute the above, which is H1 of R1. Okay, that's it. So they just proceed in this way round by round. So in each round, another variable gets sort of bound by the verifier to another random field element, and they just proceed through sum check. So in general, I guess let me try to describe, the final round, just so you can see one more round than round 1. So in round L, okay, so the prover has sort of already sent in the previous round SL minus 1 of XL minus 1. And what the verifier will do is check. That came from the previous round. So in round L, the prover will send SL, a degree 2 polynomial, and SL of XL, and the verifier will check that SL of 0 plus SL of 1 equals SL minus 1 of R minus 1. Of RL minus 1. So this is just like analogous to how in round 1 the verifier checked that the claimed answer was S1 of 0 plus S1 of 1. Right? It's just like if the prover sent SL honestly, like then SL is explicitly defined for this check to hold. Okay, like that's the whole reason we defined SL in the way we do. Remember, if the prover's honest, SL should be HL, which would be just some. So not even. I don't think there's even a sum now because so many things are bound. It should be just G of R1 to RL minus 1 XL. Yeah, so if the prover's honest, this is SL. And if the prover was honest in round L minus 1, this equality would hold. Okay, and then, yeah, so in the final round, you know, the verifier picks RL at random. And no longer, it doesn't even have to send it to the prover if it doesn't want to, because at this point, they're not going to iterate with further sum check protocols. The verifier's, you know, goal at this point is to just check that, yeah, you know, if the, you know, to check that SL and HL are the same, right? It's going to evaluate SL and HL at a random point RL. And the key point here is that HL at RL can be computed directly by the verifier because that's just a single evaluation of G, right? So I said, like, at the end of the sum check protocol, the verifier is going to have to evaluate G at a random point. Well, here it is. You know, so to summarize, in the final round of the sum check protocol, the prover sends a message SL, which is claimed to equal HL. HL is just G with all but its last variable bound already. And the verifier is going to pick a random point RL and to confirm probabilistically that SL and HL are the same polynomial by evaluating them both at RL. But HL of RL actually is just obtained by one evaluation of G. So the verifier is just going to do that evaluation. So that is the sum check protocol.
Yeah. Quick question. So the reason to start the whole protocol with, like, I forgot what you said, C equal to, like, say it's like 10 or something, is just to start that first round of, like, I guess it was like H of X1.
Let me go up to it. Yeah.
Yeah. So like you don't have to go back to that first definition of what claimed answer C is. You just use it to compute H1, X1. So it's basically saying C is what the first round should be equal to, or like how do we use C in the end?
Yeah, it's a great question. Let me actually, I have everything I need to answer it on the screen right here. So yeah, this is basically round 1 written out up to the verifier's challenge. And you could have the prover not send C. You could, in which case you would just define the claim answer to be S1 of 0 plus S1 of 1. Sorry, I wrote S1 of 0 plus S1 of 0 before. That would be equivalent. You know, if the verifier is going to check that the claimed answer equals this thing, it's also equivalent to just like assume that the check passes and set C to be the unique value that would cause the check to pass. So that would be, I didn't actually have to start with this. I could say checks that, you know, like, or V like just takes the claimed answer to be S1 of 0 plus S1 of 1. But the way I did it here lends extra parallels with how I describe future rounds, because in future rounds, let me see how far I have to go to get to it. Yeah, in future rounds, you know, I describe it as, you know, I have to tell you like what claim the prover left off with in the previous round. And that claim is basically, conceptually, I guess I didn't write it out in a very parallel way. But the prover, you know, like what the verifier is checking at the start of like round L, for example, you know, like V needs to check that SL minus 1 of RL minus 1 equals HL minus 1 of RL minus 1. That's the check that round L is like devoted to conceptually. And Yeah, conceptually, we're thinking of SL minus one of R minus one as like the claimed answer. So let me put that in quotes. And it's literally because we're using sumcheck kind of recursively, if you will. Literally each time we call sumcheck, there's a claimed answer, and this is the claimed answer for like the elf instance of sumcheck. And you know, this is sort of what we're applying sumcheck to compute. To compute this like recursively. So yeah, I started the description of sumcheck by saying the prover sends a claimed answer, and then so that there's more parallels with later rounds where there's sort of a residual claim from a previous round that the verifier is looking to check. There's a sort of a claimed answer in there. And then, of course, when I got to round L, I didn't use that parallel language, so that was not evident at all. Was that helpful?
Yes. So we're just, yeah, I see what you're saying. It's recursively. So how do you get the claimed value to start that round? I get how you can like do it at an evaluation point, and that's what evaluates the two polynomials to be equal. But like, what triggers the claim? Like, how can you compute a claim? I guess you.
Yeah, I think I can answer that. I think I can answer that. So, in a given round, let's say round J, okay, let me just come down here. In round J, P sends a univariate polynomial Sj.
Yep.
Okay, and the verifier does some consistency checks to confirm that Sj is consistent with the previous round, but let's ignore that. And at the end of round J, the verifier at the end of round J, sort of invokes sumcheck recursively to check that Sj of Rj equals what it should be, which is Hj of Rj. Okay. Yep. And we use sumcheck to compute this sort of recursively. And let's not worry about what we have to apply sumcheck to compute this, but basically we apply it to the G of R1 up to Rj, and then the variables of the thing is xj plus 1 up to xl, whatever. So this is the claimed answer, Sj of Rj, for round, or like the J plus 1 invocation of sumcheck. So the verifier is getting that claimed answer by just taking Sj, which was specified by 3 coefficients or some 3 evaluations, and evaluating the resulting polynomial at Rj. So the verifier on its own is sort of deriving the claimed answer from Sj. So the prover sends Sj, it's a polynomial. The claimed answer for the next invocation of sumcheck is Sj evaluated Rj. The verifier gets Sj of Rj itself from Sj, just evaluates Sj at a random point. Does that make sense?
Yeah, so basically it's just, so all you need is just a string of R values, basically.
Well, so, like when the prover sends Sj of Xj, remember this is, it is sort of 2 ways it would naturally specify it. I said it sends Sj of 0, Sj of 1, and Sj of, say, minus 1. And these are just 3 field elements. I don't know, just say Sj of 0 is 7, Sj of 1 is 1,000, and Sj of minus 1 is 62. I don't know. So there's a way to go, using Lagrange interpolation from these 3 evaluations to this 4th evaluation, Sj of Rj. If that's really hard for you to think about, because we only just saw Lagrange interpolation last week, and going from evaluations to an associated polynomial and evaluating that associated polynomial at a desired point Rj is just a lot to have in your head. Just think of the prover as sending Sj instead as like a plus bx plus cx squared, which means when the verifier wants Sj of Rj, it's just going to compute a plus b times r plus c times r squared, which obviously is just like 6 field operations or something. R times r times c plus r times b. You can just count. So that's how the verifier is getting Sj of Rj from Sj, which and that Sj of Rj is the claimed answer that's sort of fed into the kind of recursive invocation of sumcheck to compute Hj of Rj.
Yes, so can you use the same interpolating set every time? or do you have to change it?
No, you can use any interpolating set, in fact. Yeah, none of the security properties rely on, the prover, like, not knowing I mean, the prover can even choose the interpolating set. Like, the point, it's just a way of specifying SJ in a way that makes the proof. So I haven't even explained to you, like, why one would choose to specify, SJ via its evaluations of an interpolating set. But it does turn out to be convenient to implement the prover. And the reason is, I can say a sentence about that, right? Like, sum check remember if the prover is honest, SJ equals HJ, where HJ of XJ is sum over, XJ plus 1 up to XL and 0, 1 to the L minus J of G of R1 up to RJ minus 1, comma, XJ, comma, X1 up, XL, XJ plus 1 up to XL. So what's happening is, the definition of HJ involves summing up G's evaluations at some points, at very special points. So remember, if I'm going to specify, SJ, so if the prover's honest, SJ and HJ are the same. If I'm going to specify SJ at, say, -1, 0, and 1, I don't want to write this out 3 times, so I'll write it out just for -1. The SJ of -1 is obtained by just taking the sum, which it's so squished up there. I am going to write it again, and I apologize since it's this annoying to write out. L minus J. Yeah, so basically we just need to sum up the evaluations of G at some particular points. Those points are all of the form, right? Like the first J minus 1 values are just R1 to RJ minus 1. So they're like sort of not being changed or anything anymore. XJ we've now fixed to -1. And then we're summing over the Boolean values to the last, to the remaining variables. Okay, which means you can compute this as long as the prover just evaluates G at all points of the form R1 up to RJ minus 1, comma, -1, comma, like B, where B ranges over 0, 1 to the L minus J. And this is why it's useful. This is why it's useful, because like literally the prover, you can just say, P calls, like imagine the prover just has a function that, you feed into it a point you want to evaluate G at, and it spits out the evaluation. So P calls the function evaluate G, evaluate G at each of these points. And that will give you, the first field element of the prover's message. Okay. Whereas dealing with coefficients of SJ is just much nastier, right? It's just much nicer, like because SJ evaluated at any particular point is literally obtained by evaluating G at a bunch of points and summing the results. It lets you implement the prover by just calling evaluate G over and over again. And that's what lets me make statements like the prover time is, order 2 to the L times the evaluation time of G. Because basically in each round, the prover needs to evaluate G, so there, there are 3 of these points, and I explained each of these 3 points is, each of these 3 evaluations is obtained by just evaluating G at points of this form and summing the results. So the total number of evaluations over all rounds, total number of evaluations is sum over all rounds J of like 3 times the number of points here is just something like 2 to the L minus J, right? And actually this sum is dominated by like its first term roughly. Maybe it's 2 to the L minus J plus 1 or something. Anyway, it's dominated by the first term because it's a geometrically decreasing sum. So this is actually just order 2 to the L evaluations. That's where this claim comes from. Yeah, so hopefully that makes some sense. Like when you're implementing the prover, if you do everything, if you specify the polynomials it's sending via its evaluations over some interpolating set, then each of those things it's sending is literally just the sum of a bunch of evaluations of G, just as the original problem was defined as a sum of a bunch of evaluations of G. So that's why it's so convenient to think about the prover sending things in terms of evaluations and not coefficients. Was that helpful?
Yeah. In the R1 to the J minus one, those are not single points. Those are -1, 0, and 1 all the way through. Well,
no. So each RI is a random field element chosen by the verifier. It's only like in round J, because you're like kind of dealing with the jth variable there. In round J, the jth variable will sort of have to range over the interpolating set. Yeah, and in particular, unless G is like literally multilinear, and actually G will, it turns out, never be multilinear, and I can say something about that in a second. It'll always be degree at least 2, which means that so R1 up to RJ minus 1 in round J are just random elements of the field. And then the jth field element ranges over, definitely has to range outside 0, 1, because the interpolating set has to have size at least, 3. But it doesn't have to, it can be a carefully chosen nice set of size 3. So what we have is like the variables that are still being summed, they range over just Boolean things, 0, 1 to the L minus J. The variables that have already been bound are random field elements. So they're just like totally anything in the field. And then the variable being considered, the jth variable, well, that does have to go outside 0, 1, as long as G has degree 2 or more in that variable. But they don't have to go like over the entire field or anything. It just ranges over the interpolating set. Does that make sense?
Yeah. So and then my final question here is like, I guess, because we're trying to establish equivalence between two polynomials here. And so maybe I'm wrong, but we have to have a value for whatever jth term we're at. And we also have that, like, I guess we have the interpolating set here, -1, 0, 1. And again, maybe that's wrong, but it sounds like maybe that's somewhat right. But then what values do we plug in for X to J plus 1 to L? Is it that, do you also interpolate them over this Boolean set, or how many, like, yeah, I guess what values do we put in there in order to bound? Yeah.
So in round J, if the prover is honest, okay, then the polynomial Sj it sends in round J is obtained just by fixing the first J minus variables to R1 up to RJ minus 1 and summing over all Boolean values to the last L minus J variables. Yeah. And then, so each round, like another variable gets bound. So in round J, like at the end of round J, variable J gets sort of bound to RJ. And so, the sum in the next round will be over half as many terms because there'll be one fewer variable getting summed over. So, at that point, in the next round, variable J plus 1 will range only over the interpolating set, and variables J plus 2 up to J plus L will range only over the Boolean hypercube. And we've sort of fixed, and we fixed variable J to RJ. Yeah. So
okay.
Anyway, yeah.
That makes sense.
Yeah, great. Thanks for the questions. Yeah, it's a lot to absorb at once. Maybe next time I'll start with an example, like here's like a bivariate polynomial, and this is what happens when you apply sum check to it. I will say, I don't think it's necessary to implement this to like really get the hang of it, but that's how I got the hang of this stuff. I sat down to implement this thing, and then you really understand it and can see all of the like tricks to make the prover as fast as possible and stuff. But yeah, it's a lot to absorb. Yeah, but just as a summary, yeah, in round J, first J minus 1 variables, I've already been bound to random field elements. As I've explained, if the prover is sending evaluations of SJ over an interpolating set, that means the jth variable is going to wind up, the prover in a TED has to sort of set that jth variable to each element of the interpolating set. And then the remaining variables just range over the Boolean hypercube 0, 1, and the results get summed to define the prover's jth round message. Yeah, other questions? I know we're over time. I'm not going to cover any more material, so feel free to sign off. But I can stick around a few more minutes if anyone else wants to ask anything. All right. Well, thanks again. I hope this made sense. We'll see more sum check next week, so there'll be more opportunities to get comfortable with it. Thanks again for staying for the whole time, and I'll just stick around as all of you log off if anyone wants to ask anything. But otherwise, have a great weekend. See you next week.
Yeah, Justin, thank you. I have a somewhat random question.
Sure, go ahead.
I'm going to share, if that's okay, a page from the book.
Okay. Let me pull up the chat. I can also stop sharing my screen.
I think I can do it. Let me see if this works.
Watch stream. Loading.
This is my first time trying this, so it might not work.
Yeah, looks like it's.
Yeah.
I can also just pull it up on my screen, just on my laptop. Yeah, it looks like it's just trying to load your. It said the stream ended.
Oh, here. Well, I can just do my entire screen.
Okay.
Oh wait, it doesn't. Okay, yes, it's page 122. It's the 8.2.
Okay.
Where it's showing the circuit sat instance, and this is going back.
Yeah, I got it for the
question.
Yeah.
Yeah. So I guess what I'm getting at, or I'm trying to like wrap my head around, is if we're trying to generate a proof that some arithmetic circuit, like regardless, it could be for any computation or any logic that we want.
Mm-hmm.
Like, so we have what's called the correct transcript W for C. So this is the circuit sat, and then the values for each gate can only are bound to the finite field, and we have all the addressing here. Like, what fundamentally is the proof? Is it just like, are we like interpolating this thing on the right most where it's all these values? I'm just trying to figure out, in essence, like, what do we do with all these values inside the circuit?
Yeah. Okay. So what's happening is you take all the values inside the circuit. Okay. You and you interpolate a multilinear polynomial to fit them. So actually, I can go back to it works out well with something I wrote before today. So let me share my screen again. Should be quick. You interpret the gate values as the list of values for the polynomial interpolation. That's sort of what multilinear extensions are. So when I said the very start of the recap, I said, here we have, these values where we're saying, hey, like, 0, 0, 0, all zeros should map to V0, all zeros, but with a 1 at the end should map to V1, or what, however you want to do indexing. That is exactly how you take like this circuit transcript, like the assignment of a value to each gate in the circuit, and turn it into a multilinear polynomial. It's just that circuit transcript you think of as the interpolating values, the interpolating set being 0, 1 to the log s. Okay, and then what happens is you apply sum check not to that polynomial, but to a derived polynomial. And I said, I said today sum check, I didn't explain, but sum check never gets applied to a multilinear thing. It gets applied to something of degree at least 2. But typically that thing of degree at least 2 is obtained by like multiplying a handful of multilinear things together. And that's the case here. So you apply sum check to a polynomial. I forget what the book calls it, maybe G or H. which is not, this interpolating polynomial from the circuit transcript, but is derived from it by multiplying it by some other crap. And so the ultimate proof in the snark is just the prover's proof in that sum check protocol round by round, basically.
Okay.
Plus, at the very end of the protocol, the verifier needs to evaluate sum check got applied to some polynomial. I don't know, let me call it G, and the verifier needs to evaluate G at a random point. And the sum check protocol in the snark was applied to a G that was, derived from but not equal to the multilinear extension of the witness of the circuit transcript. Like, let me call it W tilde. So basically, to evaluate G at this random point, it turns out, up to some caveats, evaluating G at this point, it's enough to evaluate W twiddle at a few points. Let me call it R1, R2, R3. And in the snark, W twiddle is actually committed with a cryptographic commitment scheme, and the commitment scheme used comes with a mechanism for the prover to actually provide, even though the prover is not trusted, to provide these three values to the verifier. So that's really it. So the proof is the sum check proof plus the cryptographic information, allowing the untrusted prover to provide this information about the circuit transcript to the verifier to then let it evaluate the polynomial that sum check was applied to at the necessary random point. Does that make sense?
Yeah. So W tilde is that the polynomial that you're referring to, that like it's like crap plus or multiplied by what we're interpolating here from the circuit stat? Like is that where W tilde originates from?
Yeah. This W tilde is just, there's probably, I forget exactly how I covered in the book. There might be a nuisance in terms of adding like the public input to it or something. If you assume that there just like is no public input for simplicity, W tilde is literally like, take the circuit transcript, that is the value assigned to each gate in the circuit, interpret them as like the values that some multilinear polynomial takes at each of the Boolean hypercube inputs, and W tilde is that polynomial. It's the polynomial with that like input output behavior over the Boolean hypercube. Yeah.
Okay. So if you had a Boolean hypercube of say like 4, so like 0, 1 to the 4.
Yeah.
I think we have in this example on this page 122 in the book. Then how many polynomials would be generated from that?
It's just one. So if the circuit has size 16, then you would be assigning conceptually like each gate a 4-bit label, because there's 16 bit vectors of length 4.
Yeah.
And you would just interpolate, based on,
Okay.
So figure 8.1 in the book, which I have in front of me, is exactly telling you like what W tilde is, just through like multilinear interpolation of this W. And then all the snark is doing is applying sum check to a polynomial that's not W twiddle itself, but is like something derived from W twiddle. And so the snark proof is just like the transcript, like all the prover messages in the sum check protocol, followed by a little bit of extra information that comes from the cryptography used to commit to W twiddle to give the verifier the information it needs to evaluate, the polynomial being summed at the necessary random point.
Yeah, it does the PCS on W twiddle.
Exactly.
And then it uses the IOP using fiat Shamir to make sure that it is agreed. And I'm like, I'm getting a little ahead of myself.
Yeah.
My understanding, but
it's okay. And the IOP really just IOP. It's a lot. I find it a little frustrating, the terminology, because there almost is no IOP here. The only reason it's just sum check and a cryptographic commitment scheme. So and the only thing being committed is this multilinear polynomial W twiddle. So people use the phrase IOP to sort of indicate that W twiddle has been committed, basically. But that's all that's happening. It's literally just the sum check protocol we saw today, combined with a commitment to W twiddle, so the prover doesn't actually have to like send a description of WTwiddle to the verifier, which would not be succinct because WTwiddle's description is like, one value for each gate in the circuit. Yeah.
Yeah, and Fiat Shamir is not even involved in anything that we just said. So I hear you.
Right. Yeah. Fiat Shamir just comes in at the very end to take the interaction away from some check. That's it. Yeah.
Yeah, got it. This actually makes some sense. Yeah,
Good.
yeah. This is awesome. I'm like super appreciative of this. Yeah, I have not a little project, but basically we're trying to go from. I asked you the question about front ends long ago, but like trying to now that I know like what these gates are doing, getting like I'm trying to build my first Planck circuit, and and I don't know if there's like an exercise that you recommend to build a Planck circuit like the Fibonacci is like a classic example, or this is like if you had students, like what would you give them to build their first Planck circuit?
Yeah. No, I'm not as up on the tooling since I'm not, building these things myself these days, but I do have students who have dealt with this recently. I mean, in this ZK MOOC that Dawn organized on Song, and like Dan was pretty firm, Dan Bonnet, that he has students up and running with CIRCOM, in like a matter of days.
Yeah.
So that was his recommendation. I forget which libraries support Planckish and which don't. Does CIRCOM support Planckish?
I don't think it's R1CS only. So that's my problem.
Okay. So then, Halo 2 supports Planckish, and I think, in fact, it doesn't come with the front end. It like kind of makes that. This is my understanding. It sort of makes the developer write in Planckish. So if you want to get comfortable with Planckish, that's maybe the perfect thing, I guess. People seem to like it.
Okay. Yeah, I actually know Jordi and Jose Luis Munoz. Like, so I'm starting to like talk to them about this quite a bit for the project. So it's interesting. I'll figure. I'll let you know because CIRCOM is R1CS only, and I'll let you know if there's a different library that Jordi recommends as my project progresses.
Yeah, that'd be nice to know. Yeah, I think Halo 2 is definitely a decent choice, but if there's a better one, that's definitely good to know. So please do let me know. Yeah, and I'm working on some stuff that I hope will unlock some new front end techniques. It's really like back end work, but it like enables new front end techniques. So I'll try to tell you about that as soon as I can. Since you're looking into, I guess, these front ends so seriously right now.
Yeah, for sure. That'd be amazing. Thank you so very much. This has been incredible.
Of course. Yeah. Thanks for all the questions. I think they're super helpful to ask them. So I appreciate it.
Cheers.
Yeah. Have a great weekend. See you soon. Bye. Any other questions?
So the Oracle access in the end, like, you can use basically any polynomial commitment schemes. But like, so what's usually used?
They all just come with their own trade-offs between, transparency, post-quantum security, prover time, verifier time, proof size. But the most popular ones today tend to be KZG if you're dealing with univariate polynomials, Fry if you're dealing with univariate polynomials, bulletproofs, which supports both multilinear and univariate. Those are the popular ones today. They are the most popular primarily just because their proof sizes are the smallest. So I think with, composition and stuff, I don't think that they will forever be the most popular is my personal take. Does that all make sense?
Yes. And so what's some example systems that use univariate sum check today? Maybe.
Yeah, the main ones are just Marlin and Planck doesn't explicitly use univariate sum check, but it does use univariate polynomials. And they both use KZG commitments. And basically, my view of that is the main reason to use univariate polynomials is because Sum check itself that we saw today has 1 round per variable, which means you'll never get the proof size below like the number of variables. So if you use heavily like multivariate polynomials with lots of variables, you never get the proof size below, all that small. Now, I don't think it really matters that much. For example, like Fry has log squared size proofs with a nasty constant. And so like, using sum check applied to a log variate protocol is going to have much smaller proofs than Fry. So I don't actually think this is a real issue. But anyway, if you use univariate techniques, you can hope without recursion to get the proof size to be constant, because you have like a constant round protocol instead of a super constant round protocol. But then you want to use a polynomial commitment scheme where the evaluation proofs are also of constant size, because a constant round protocol with a polynomial commitment scheme that has super constant size proofs still does not give you constant size proofs. So basically, Marlin, Planck, and essentially Growth 16 too, they all use univariate polynomials combined with KZG to get these constant size proofs, constant number of group elements. Starks also uses univariate polynomials, but they use Fry. So, I suspect, although I don't have performance numbers quite yet to prove this, that something sum check based with Fry would be superior to what Starks are doing with combined with Fry. It's like just take the sum check thing and use Fry as a polynomial commitment adapted to handle multilinear polynomials, rather than doing the non-sum check based thing that Starks are doing with Fry as the polynomial commitment, if that makes sense. But that is a personal opinion and guess, let's say, until I actually have like an apples to apples performance comparison, which at some point I'll get around to doing, I guess. Does that make sense?
Yes.
Mm.
Yes. Thanks. And like, so by the way, like if you want to write like Planck circuits like easily, so like NOR is like a high level one, and so you can write Halo 2 Planckish stuff through Halo 2 as well, but I'm actually working on like connecting NOR through Halo 2, so hopefully there will be like.
I think that'd be great, because I think Halo 2, like its usability by non-experts will go up, and just in general, if it has a front end, and I do hear good things about the NOR front end. If you actually wouldn't mind putting that in the chat, so that the person who asked the question, who might not be on the call anymore, sees it. I guess NOR is like higher level than just like kind of writing out the Planckish constraints directly, but that's probably a good thing. So yeah, if you wouldn't, that's a good suggestion if you wouldn't mind putting it in, and I'm excited to see the integration if you complete it.
Yeah, and I think the NOR link is in like learning resources just now. So like Anna like posted it. So
yeah, that's great. I think and that makes sense. I guess it's not, there are a lot of discords and I find them very hard to keep track of. So it probably doesn't hurt to resurface it in the study group, this study group's Discord too, I guess.
Okay.
Cool.
Yeah. So okay. I don't have any other questions.
Okay.
Thank you.
Yeah. Thank you. All right. I'm gonna guess have a great weekend. Any more questions? Get them in quick. And if not, I will log off and see you all next week.